This is question 12. For this question, we have a lot of things to do. So first, we need to design an up-based Miller integrator circuit, which provides a unit gain at 100 kilohertz and has an input impedance of 1K. So we need to draw the circuit diagram and prepare the body table and draw the body plots. Okay, so the body table itself, I won't show you here. I'll just draw the body plots. You can check the values of the body table using like the solution manual. For the above circuit, for the above design circuit, in the passband region, if it's desired to limit the DC gain to 60 dBs, what type of component would you add and where you will add it, and design its value meeting the requirements. So what's the 3 dB frequency of the design circuit, this new circuit, and we draw the corresponding diagram and prepare the body table and draw the body plots, and what type of filter function does this circuit represent. So once we basically limit the DC gain. So first, design an MPL-based Miller integrator. So if you recall, so let's call this part A. Okay, so a Miller integrator using op-amp is just a resistor here. Then we have our circuit. So this is the inverting input, the non-inverting input, we can just ground it. And then here we have a capacitor. Okay, so here's our VI. This is our V out. This is R. This is C. Now, one of the things that it says in the problem is that the input impedance, it should be 1K. So the input impedance, if you look at the circuit, right? So this is 0 volts here. The input impedance is exactly the R that we have connected to the input, right? Because if this is, so if here is 0 volts, because the non-inverting input is grounded. And remember, for an ideal op-amp, V plus is equals to V minus. So the current here goes directly to the 0 volts, right? So the input impedance of the circuit itself, Rn, is equals to R. And because we want an input impedance of 1K, this means that R is equals to 1K. Okay, so that's the first answer. Now, we want to provide a unit gain at 100 kilohertz. So the voltage transfer function for this particular circuit, H, okay, or the magnitude of H, is equals to 1 over omega CR, right? So we know that we want a unit gain, so this is 1 equals to 1 divided by the frequency that we want is 100 kilohertz. So remember that here is angular frequency, so we have to multiply by 2 pi times 100K, right? Times C times R. So the value of R we know, we just need to define the value of the capacitor that gives us that unity gain at 100 kilohertz. So if we just manipulate this equation here, this gives us a capacitance, so we just put the capacitance here on the left hand side. This gives us a capacitance of 1.5915 nanofarad. Okay. So for part A, we have designed the Miller integrator, okay, providing the gains and stuff. Now, for the body plot, let's call this part B. So let's call it, let's call it part B. Down here. So for the body plot, so we know that the phase, right? So the phase of this circuit, it stays at 90 degrees, okay? Phase is equals to 90 degrees. And the magnitude, we have the magnitude for this circuit that is equals to 1 over omega CR. So if you want to plot the Bode plot, we can plot here for the magnitude. Okay. And the phase, you see that it stays constant. Okay. So the phase here and the magnitude j omega in dB. So for this particular plot, you have on the solutions the exact values, but the thing is that exactly at 1 over omega CR, right? So this is when omega is equals to 1 over CR, we have the unit gain. So a unit gain in dB means 0 dB, right? And because this is the magnitude, and because this plot here, it increases and it basically decreases by 20 dB per decade. If we have over here 10 times 1 over CR, we will have minus 20 dB. So let me draw minus 20 over here. And 0.1, so 1 decade earlier, over CR, you would have something that it's 20 dB. Okay, so we have this point here, 0 here, and then we have this one here. So the magnitude follows this trend here with minus 20 dB per decade. And for the phase, we just have 90 degrees here. So if we have the same ticks here of 0.1 over CR, 1 over CR, and 10 over CR, it's just constant at 90 degrees. Okay, so you see on the solution manuals that we basically have some values for like 1 over CR. You can calculate it by plugging in the values that we calculated in part A, but that's the overall trend of the Bode plot. Okay, now for part C, we need to define a finite gain. Okay, so for part C, we have to define a finite gain. Okay, so to get a finite gain, the solution would be to put a feedback resistor in parallel with the capacitor. So the circuit that we would have is just a resistor here, goes again to the negative, so the inverting input. This one here is grounded. Here's VI, and then we have the capacitor here, C. Right, so this is R, this is C, and then to limit the DC gain, we just have to put another resistor here, right? So this is RF, and this is V out. Now, so how do we limit the DC gain, right? Because if we now analyze the circuit here, so let's do a quick analysis. First, we know that V plus, so this voltage here is equals to 0 volts, which implies that the voltage here at this node, V minus, is also equals to 0, right? And remember that we are going to perform an analysis in the frequency domain. So we have to convert this capacitance to a reactance, right? And this reactance, it becomes, so XC, it becomes 1 over J omega C, right? So the current here that we have flowing here is just V minus VI divided by R. So it's V minus VI divided by R plus V minus V out divided by the parallel between the resistor and the capacitive reactance. So this means that we have RF times 1 over J omega C divided by RF plus 1 over J omega C, and that should be equals to 0, right? So if we manipulate this equation here, we get that, so first, minus VI over R, this is for the first term. Then we know that V minus is equals to 0, so this one here becomes 0, right? This one here becomes 0. And then we have minus V out, okay? And then here, this term here on the denominator goes up there multiplying, so it's times RF plus 1 over J omega C divided by RF times 1 over J omega C, and that's equals to 0. So we can simplify even more this equation by multiplying multiplying this term here, the second term of the equation, by J omega C, and here on the denominator also by J omega C. So it's the same as multiplying by 1, this second term, but it simplifies the equation. So we get minus VI over R minus V out, and then this J omega C times J omega C becomes 1 plus J omega C RF for this multiplication divided by just RF, right? And this should be equals to 0. And if we isolate V out over VI in this equation, we get that V out over VI is equals to minus RF divided by R times 1 plus J omega C RF. So that's the voltage transfer function, okay? This is equals to H of J omega, right? Now at DC, right, at DC, so if we calculate at DC, which means omega equals to 0, and we calculate the magnitude just to get the gain, because remember, on this part we want a finite gain of 60 dB, right? The magnitude of H of J omega overall is equals to RF, because that's the magnitude of the numerator, minus RF becomes just RF. And then here we have R times the square root of 1 plus omega C RF everything squared, right? But if we want that at DC, this magnitude of H at 0 is equals to RF divided by, now because this term here it's omega CRF, if we get omega equals to 0, it just becomes square root of 1, which is 1. 1 multiplied by R is just R. So with this equation here, we can calculate the value of RF, okay? Because we want a finite gain, and the finite gain is 60 dB. So 60 dB, if you want to convert to linear, is just 10 to the power of 60 divided by 20, which is 10 to the 3, which is equals to 1000 volt per volt, okay? Now if we substitute this 1000 here in this linear equation for the magnitude of the gain, we get 1000 equals to RF divided by R, which in our case is 1K, and this leads to RF equals to 1 mega ohm. So this 1 mega ohm resistor that we insert over here limits the gain at DC to 60 dB. Okay, so if you go back to the body plot without the resistor, you see that if we go at DC here, we keep increasing by 20 dB per decade. So eventually that gain will become like very high, something like close to infinite at zero, right? But if we put like this feedback resistor, we limit that gain at DC to be exactly 1000 or like 60 dB in the dB scale of the body plot. Okay, so that's part C. Now for part D, we need to identify what's the 3 dB point that corresponds to the frequency where we need to define the 3 dB point, right? So the 3 dB point, so let's call it part D. Okay, the 3 dB point is where the magnitude of the voltage transfer function, it's 3 dB lower than the gain at DC. So remember that for this particular case, this 3 dB gain, it sometimes it needs like you have to analyze if it's like an integrator, differentiator, or what's the circuit that you are analyzing. But in our case, we have this DC gain that it's 60 dB, and our 3 dB point is going to be the point where the 60 dB becomes 57 dB. So you see we went from 60 dB, so we decreased by 3 dB, and we reached 57 dB, right? Which in a linear scale, so this is dB, right? In a linear scale, this 57 dB corresponds where the magnitude of J, the linear, is equals to 10 to the 57 divided by 20, which is 707.94 volt per volt. So see, we decrease the gain by 3 dB. Okay. And now, because we know the voltage transfer function, the magnitude here, this is the equation, right? So we can just plug in the value of the magnitude, right? The linear magnitude, and then isolate omega out of that equation. Okay. So it ends up that, so H, I'll just write H to simplify, is equals to RF divided by R times the square root of 1 plus omega C RF squared. So if we squared both sides of this equation, we get H squared, which is the gain, right? This is the magnitude squared, is equals to RF squared divided by R squared times 1. Now we get rid of the square root, plus omega C RF squared. Okay. And then if we basically, so this is close parenthesis here. So if we multiply the denominator here to the left hand side, H squared, we get H squared times R squared plus H squared times omega squared C squared RF squared equals to squared RF. Okay, and now we can just take this omega squared equals to RF squared to the power 2 minus the magnitude of H squared times R squared divided by the magnitude of h squared times c squared. I think I forgot, so because we have this r squared here, so we still have r squared here. So c squared rf squared times r squared. Okay? And once we take the square root of the right hand side, we get our omega. So it's just a matter of substituting the values that we know. So omega here becomes the square root. Remember that the 3 dB gain is going to happen when we have this gain here, right? The frequency at 3 dB is going to happen when we have that gain. So for RF, we know that we have 1 mega ohm, so this is 1 times 10 to the 6 squared is 10 to the 12, okay, minus the 707.94 squared times 1k squared, which is 1 times 10 to the 6, divided by 707.94 squared times the capacitance squared. So this is 1 point, let me go back to see what's the value. So the capacitance is 1.59, right? So it's 1.59 times 10 to the minus 9 squared times 1 times 10 to the 12, because it's 1 mega squared, times 1 10 to the 6, because that's r squared. So let me just erase this square root here and write it as square root of this entire thing here, which gives us an omega that it's 626.85 radians per second, or a frequency that it's roughly 100 hertz. Okay, so that's the answer. So just quick recall. So we know the voltage transfer function right here. We know that the 3 dB point for this particular circuit is going to happen when we have 60 dB minus 3 dB, so exactly at 57 dB. Then we manipulate the magnitude of the voltage transfer function to isolate omega. Right here we isolated omega squared, but it's just a matter of taking the square root. Once we plug in the values here, we get the magnitude, the frequency that we have exactly the 707.24 volt per volt gain. Okay, and now part E is just drawing the Bode plot. Okay, so for the Bode plot, you can create like a table. So in my case, I went from 1, 10, and then I also include here 626, because that's exactly the point of interest here for the 3 dB point. 1k, 10k, and then 100k and 1 mega. Okay, so we can calculate the magnitude in dB. That's for the magnitude of the Bode plot, and also the phase. Okay, so if we substitute this omega in the voltage transfer function here, so let me go up there. So in this voltage transfer function here, okay, you get a complex number. For that complex number, the magnitude, okay, it's going to be the first column here. Then you just have to convert that to dB, which is 20 times log 10 of that. And the phase of that number is going to be the phase that we are going to plot in the Bode diagram. So the results that I got was at DC, so for 1 here, the phase is close to 180 degrees. then it starts reducing to 179, and then for 626 it goes to 135, 1K it goes to 122, for 10K it's 93 degrees, and for 100K it's 90.36 degrees, and 1 mega ohm is roughly 90 degrees. Okay. And for the magnitude, so it stays at 60 dB here, which would be expected. Like for lower frequency, we stay at 60 dB. So this one here, exactly the 3 dB point, so we know that it should be 57 dB. And then we start decreasing by 20 dB per decade. So it's 40 dB here, roughly 40 dB. 10K, it's 20 dB. 100K, it's 0 dB. And then here is minus 20 dB. Okay, so if we take these values and then plot in the Bode plot, so we can draw the Bode plot here. So this is 60, then we have 40, then we have 20, and here minus 20. So here's the magnitude in dB. We have 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 4, 5, 6. Okay, so this is omega. Here it's 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4th power, 10 to the 5th, 10 to the 6th. So we know that for lower frequencies we have at up to 10 to the 2, right? So we stay at 60 dB. Then around here at 600 and something, so it's close to the end here. It's a little bit lower than that, right? It's 57. Then at 10 to the 4, it's just 40 dB. So here it's roughly 40 dB. At 10 to the 5, it's roughly 20. And then here at 10 to the 6, it's minus 20. Sorry, at 10 to the 6. So let me just... So 10 to the 3. Oh, exactly at 10 to the 3 is 20. So yeah, I thought there was something wrong here. So see, it goes to the 40, and then here is 20, here is 0, and here is minus 20. Yeah. So this is the magnitude, okay? So here it's minus 20 dB per decade. Okay, so remember the difference between the first configuration that we have without the feedback resistor. In that case, the voltage transfer function would keep increasing here, right? So we would keep increasing here. But because we have inserted that feedback resistor, then we are basically limiting the voltage gain at lower frequencies. Okay, so we don't go anymore to infinite dB at DC. Okay, and for the phase, so we can say that here we have 90 degrees, here we have 180 degrees. So this is the phase, and we can plot the same values here. So we start at, so this is just the same, so I won't draw the entire thing. So it's 180. This is a little bit less than 180. Then exactly here at, so this is 10 to the 0, 1, 2, 3. So exactly around here we are at the middle, right, at 626. So this are just called 626. We are at 135. Then at 10 to the 4th we are 10 to the 3 exactly, we are a little bit less than that, so we are around here, 122. Then here we are 90 degrees, and then eventually we get to 90 here. So this is the phase. Sorry, I think we should have one more value here that's closer to 180. It goes just right like that. So you see that at higher frequencies, we still have the same 90 degrees that we have on the first circuit. But now, because we have inserted that feedback resistor, we have changed the phase. Also, we have changed the phase for lower frequencies. So it goes from 90 up to 180 once we go for lower frequencies. Okay. Now, for the last part, which kind of filter does the circuit implement? So if you look at the drawings that we have here for the Bode plot, for lower frequencies, we are actually amplifying by 1,000, right? So over this region here, lower frequencies, we are letting things be amplified. But once you go to higher frequencies, so especially at this region here onwards, right? For higher frequencies, we are attenuating. So this circuit here, it behaves, so part F, if you wish, this circuit, it behaves as a low pass filter, okay? Because it amplifies lower frequencies, but it attenuates here, because once we go to minus 20 dB, it starts to attenuate the input voltage, okay? So that's it for this problem.